Alright, so I thought I'd show current status of where we're at. So basically on this page is my foundation of mathematics, and unlike something like piano arithmetic that only takes us through addition and maybe multiplication, other than that becomes fraught because problems with the naturals that nobody ever recognized somehow. Hi. This goes all the way through calculus. Alright, so 0 is your universal origin. All dimensions have 0, and 0 has no dimension. So if I tell you that there's just no raccoons over there, this implies that there's also no giraffes, right? It's not the sort of implicature that you're used to thinking about, but if somebody says there's no raccoons over there, you're not going to think that there's giraffes. You're not going to think that there's aliens. You're not going to think that there's 27 basketball players, right? So if I say there's no raccoons over there, that actually implies that there's nothing of interest over there at all. On its own, that's what that implies. Alright, now a dimension is a type linear space emanating from 0 in 2 directions. Okay? So the type of a dimension is the dimensional unit, and different types have mutually perpendicular dimensions. Okay? So dogs and potatoes are perpendicular to each other. Right? If we're going to plot something like how much money is earned per magazine sold, right? Money and magazines are perpendicular to each other. Right? This is basic. Alright. Order only arises if both directions emanating from 0 within a single dimension are treated unequally. Okay? This is important. The disfavored direction is positive. The disfavored direction is positive, and thus falls after the favored direction, negative. Thus, negative has precedence over positive. We can show that negative is favored by noting that negative of a negative is positive, allowing us to derive both directions from just negative. But the negative cannot be similarly derived from positive. Like how negative is more fundamental than positive. Negative can beget positive by negating itself. Positive cannot beget negative, no matter what it does. Okay? This is the source of order. Magnitudes are distances from 0. 0 itself is not a magnitude, and by extension, it's also not a number. Okay? So this is, in a large part, this is a return to Eudoxus, or Cneidius, where he basically saved mathematics from the Pythagoreans. The Pythagoreans wanted to call everything they saw a number, and that turned out to be a problem. So Eudoxus came in and he's like, okay, we got the numbers. 1, 2, 3, 4, 5, 6, 7. We got that shit. But there's also just magnitudes that we can work with. And then we look at ratios between those magnitudes so that we can compare them and we can usefully construct things. And this is how we got classical Greek geometry, right? Euclidean geometry. This is how it came about. And then later on, the development of algebra went back to the Pythagorean idea that everything is a number. And the logicists took this to an extreme that just broke shit. It was already broken by algebra because there was a return to that original problem that Eudoxus solved. Anyway, so any magnitude can serve as the reference for this comparison. So these guys, pi, phi, root 2, these are magnitudes, but they are non-numbers. Okay? Magnitudes can be compared to each other only within a single dimension. Right? So 7 giraffes and $7 have the same magnitude, but they cannot be compared to each other. Asking which is larger simply makes no sense because these two magnitudes have completely different units. Magnitudes can be accumulated to reach further away from 0, right? So we start at 0 and we're in the imaginary dimension, right? And we're +3 away from 0, and then we go +5 away from that. That's 8 away from 0. If we go in the negative direction, -3 away from 0, and then -5 away from that, that's still 8 away from 0, right? That magnitude is the same. So this distance, it is fundamentally unsigned and dimensionless, which obviously means it's not a natural number. So this is a category of object that doesn't even exist under set theory, because when you need an unsigned number under something like Zermelo-Fraenkel, you will claim that it's a natural number. The problem with this is that the way the natural numbers are defined, they are the non-negative integers. So they are signed, so because they're positive. So there's an inherent contradiction. There's a problem there. You can't do that. Alright, so numbers are a special collection of such distances from 0 made from accumulating the dimensional unit. Okay? So there's some examples. Note that this is not the successor function, as it derives from more fundamental dimensionally bound ordered magnitudes. I'm also not mapping anything like the successor function to anything else. This is the problem, the base problem with like Peano axioms, is the successor function has this built-in order, and it's mapped to the naturals. But then when Gödel comes along and shows incompleteness by using Gödel numbers, which are nominals, which are unordered, nobody bats an eye. And the reason is the naturals don't actually have that. They're not actually ordered, unless you want to invoke the order. If you're using ordinals or cardinals, you want that order. That order is interesting. But if you want to use them as nominals, as in Gödel numbers, or many other uses, that order disappears. Which means that mapping the successor function to the naturals was a mistake in the first place. That's the source of the problem. That's the reason that you're allowed to get incompleteness. Because without Gödel numbers, incompleteness doesn't exist. But Gödel numbers are coming from manipulating this contradiction at the heart of the definition of naturals. Okay. Now, vectors, these are a combination of magnitude and dimensional units. So root -2, 17 divided by 3, and 12 cats. These are all vectors, not numbers. Okay. And I don't think anyone would argue that 12 cats is not a number, but pretty much everyone would argue that these are numbers because of the dishonest way that mathematical jargon works, right? We'll say that this is a number. But look at it. What does this mean? What does the denominator mean? It means it's the denomination. Denominator is indicator of denomination. Denomination is synonymous with unit. What is this part? This is the numerator, the indicator of the number. The numerator indicates how many of this denomination we have. This is a combination of number and unit. This is not a number itself. It is a vector. It has a magnitude and a unit. The same here. This negative is a unit. So this root 2 on its own is a magnitude, but root -2, it now has a unit because of that dimensional reference back to negative. Okay. Comparators. So I added a few and I changed the notation slightly. The fundamental reason that I changed the notation is because I want to be able to contrast what this is producing versus what something like Zermelo-Fraenkel is producing, or something classical is producing, because there is now enough differences that it becomes important. So equality, instead of the double bar, it's the double dot, right? And that actually ends up being nice, because so we can collapse this into things. And I also added between, right? So every natural language that I can find, that's even natural languages that don't have numbers, have the concept of between. But I can't find any formal mathematical language that has this sort of thing, right? So here's the leftward anaphoric inequality and the rightward anaphoric inequality. So leftward anaphoric inequality means that the things that you're between come first, and then, right? So 2 is between 1 and 3, and 1 is the smaller of the two, right? Here, 3 is bigger, so it's indicated 3 is greater than 1, but between those is 2. 2 is between, and these are positive, right? I'm being lazy. Positive 2 is between positive 1, which is less than positive 3. It's between those two values, right? And we also can indicate unknown relations. So bear 2 cannot be compared to bear 3. If we want to do an inequality, or an equality or a directed inequality, we can just append the equality onto it. So these basically look like the classical ones, but with dots. Anyway, arithmetic. So this describes generalized accumulation. Literally, arithmetic means counting. Okay, so naive magnitude accumulation is summation. So here is this notated. Right, so here's the classical notation. So 4 plus 3 is the same as 3 plus 4, and that's 7. 4 minus 3 is the same as negative 3 plus 4, and that's 1. And here this is much more carefully and explicitly outlined here. Patterned magnitude accumulation is multiplication. Classically, this is where arithmetic ends. And I've always found this strange because there's stuff beyond multiplication, but this is where arithmetic ends. And for some reason, this is what everyone was really obsessed about acquiring correctly from Peano's axioms, or something commensurable with Peano's axioms. But leaving multiplication out, as in Pressburger arithmetic, solved the problem of incompleteness. So it was left out. Even though all you're doing is, if you have addition, you also have multiplication automatically. Like, what the hell are you doing? Anyway, patterned magnitude accumulation is multiplication. Naive magnitude accumulation is summation. Okay, so if I just keep adding the same thing to my initial reference, that's the same as multiplying. That's all that is. Right, so here I start at 12 and I keep subtracting 4s. Oh, look at that, I get to 0, and oh, there's division. So division is unintuitive because the solution is the number of iterations, not the ending point. So here, we start at 0, we keep adding this vector, and our endpoint is our solution. Division, we're actually counting the steps. That's what it is. So this guy right here is our solution. Pattern multiplication is exponentiation. Right, so here our initial condition has to be 1. And as long as we set that condition, anything to the 0 power is 1, by definition. And if we don't set that initial condition, if we set the initial condition to anything else, no other exponentiation actually works anyway. So we have to set this initial condition to 1. And if we do that, it actually explains why 0 to the 0 is 1. Always. Doesn't matter what the limits look like. It's always going to be 1, which is classically inexplicable. Like, you cannot do this with Zermelo-Fraenkel. You cannot do this classically. But it's actually trivial. if we just pay attention to how shit should work, right, and we note what our initial conditions should be, it ends up working correctly. That's how hard this shit is, right? Also, anyone criticizing this, I'm like, that's not what I was taught. I don't care. You're an idiot. Okay. Now, logarithms find the number of iterations for multiplication, just as division does for summation, right? So logarithms, you're looking at this guy after the repeat operator. And this is genuinely an operator. That is genuinely an operator. I'm going to show in a minute that, well, so addition, the plus sign, this isn't an operator, 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 not really. This actually is. Right? What this is doing, if anything, if you want to call it an operator, it's appealing to this. This is your fundamental operator. This is just a higher level notation indicating a particular structure for it. Same thing with this. Alright. Now, ordered lists are the natural output of exponentiation. Right? So this guy, 1, 2, 3, dot 4, 5, 6, with respect to 10, is the same as 123.456. Okay, because we're using base 10, we get 123.456. Okay, here's a quadratic. A comma b comma c with respect to x is ax squared plus bx plus c, or cosine theta comma sine theta in unitary terms, right, is the same as cosine I sine theta, because this guy is perpendicular to this guy, and this guy is your unit that you're choosing. So this guy being perpendicular to your unit is its unit is I automatically. So that gives you this. Okay? Now, calculus describes dimensional accumulation. I haven't shown this yet, so this might be wrong. But I think this will end up giving us all of abstract algebra. Already it's definitely given me a lot of it. So I think this might be hyperbole, and at this point it is conjecture. But it might be real. I'm not sure. We'll see. Anyway, so now we can move on to calculus. Okay, so over here, extending the power rule. So here is this list, this ordered list, right? This base 1 polynomial is what these are, okay? So this is, here's our reference point, here's our decimal, and then what these values are is the inverse of our index, right? So index 0 is 1 over 0, index 1 is 1 over 1, 1 over 2, 1 over 3, right? And that repeats forever that way. Over here, negative 1 index is 1 on negative 1, 1 on negative 2, 1 on negative 3, repeats forever this way, okay? So this I'm going to assign to zeta. Now, these are out of order. Developing it on the fly. Anyway, so we have some function of x. We're going to assign that to z0. Now, we're going to stick z0 into zeta. Okay. The way this is going to happen is kind of weird though, right? So zeta is mapped to z overall, but z0 is a function of x of order m inserted between zeta sub m and zeta sub m plus 1. Okay, and we'll see that later on why that works. But also note there is a singularity here, because this cannot be evaluated. The inverse of 0 cannot be evaluated. But also, note what this position means. This position means that we are perpendicular to our unit, which is exactly what this is. So this is correct. Now, over here, we can define our x, right? So x naught is 1, everywhere else it's this variable. Alright, so z naught, this is the unified equation right here, which gives us multiplication, division, exponentiation, logarithms, and integration and differentiation. This is what this is, right? So this is setting us up for this. This is a specific instance of how like the power rule works and other things. But plug this in, we can see how this works. Alright, so integration here. Integration moves down the page. So we're taking the integral of 6x to the negative 4 dx. That's going to give us negative 2x to the negative 3 plus c. The main term of dx is z to negative 3, this. Negative 1/3. And that's being multiplied by x. Right. And we can continue integrating here, and we can cross with integration. We can cross the singularity. We can come all the way across here. We can do this, or we can start somewhere over here and just carry on that way. Right. So integration moves this way, right to left in this structure. Differentiation goes the opposite direction. Right. So here, the main terms, they are I mapped these so they're the same, right? They're next to each other. But here we have a multiplication, and here we have a division by this same object. Okay. Now differentiation cannot, if it starts over here, it cannot cross the singularity. What ends up happening is it falls into an infinite loop. So if we notice, if we try to take the derivative of these guys, it ends up just getting stuck here. It cannot cross this. Okay. So I named this based on Xiangqi, right? So here we have Hanjie. So integration, because the Hans won that conflict, that war, the Hans were able to cross their border. Hanjie is not impenetrable, but Chuhe is. So differentiation stalls here. Can't go any further. From here, you can differentiate this way. Right? Differentiation moves this way. Integration moves this way. They're just inverse of each other. Okay. Differentiation moves this way, and it gets stuck at the singularity. If it starts over here, it's fine. It can go off forever. Now, integration crossing the singularity, the way that it does this, because we can't evaluate this inverse of 0, we need to rederive our dimension logarithmically. So fundamentally, that's what this is. That's what these values are. The reason that this is a 1/2 here, let's see, here, is because we're moving into a space where our original dimension is, if we take the logarithm of the space that we're currently in, our original dimension is 1/2 of that, right? The logarithm of our current space. Logarithm base current space of our starting space is 1/2. That's how you say it. That's what these numbers are. That's what they're indicating. Okay. So fundamentally, that's what we're doing all along. We're taking a logarithm. Okay. So integration can cross the singularity by using a logarithm. The integral of 1 on x is ln x. It's a logarithm. This is correct. This is behaving correctly. But then you get some other stuff, and notice that this constant of integration is appearing. Here I didn't write it. Here I didn't write it, but it's there. The reason it's appearing is because when we integrate this, we get something out of it. But it's unpredictable because we can't evaluate the inverse of 0. So everything about this is behaving as it should. all of the details about this inverse of 0 here are behaving correctly. It is well behaved. You can't evaluate it, but that's not really the problem. The problem is, historically, it was determined that it can't be evaluated, so it was just ignored. But it's actually driving a lot of the structure here. Okay. So differentiation stalls at the singularity because it falls into an infinite loop of dividing by the inverse of 0, which is equivalent to multiplication by 0. Integration can cross the singularity by using the logarithmic definition of the dimension x in order to solve the multiplication by the inverse of 0. This is equivalent to a division by 0. Note that we can always interpret the constant of integration as the consequence of this division by 0. Now, note that integration from the singularity is a special case of generalized integration revealed when we consider how integration across the singularity works. The nature of this special case is as follows. In dimension 0, ln x is 0. This happens when x is a dimension in our existing reference frame. In dimension 1, ln x equals 1. Note the relationship this has to Euler's formula. In dimension 2, ln x is 3/2. In dimension 3, it's 11/6. And I think it's going to carry on with this sequence, but I haven't actually verified that yet. I should, but I haven't. A better approximation of the perimeter of an ellipse, leveraging logarithms over functions. So this is from a previous video. I noted this when I found this on January 20th. But if we just take that, so we start here, basically, and then we just come out to the triple integral. So there. Yeah, that one. We end up with this function that is really, really accurate, unreasonably accurate to giving us the basic, this part, component of the perimeter of an ellipse. But now notice that this derivation requires recognition that d dx is not an operator, but simply a vector under algebraic manipulation. Zeta is the d on d component of the vector, which is obviously incorrectly named in Leibniz notation, because this should mean 1. It isn't. It can be 1, but it's usually not. Alright, now, if we finish the thought, we end up being able to fully derive Leibniz notation without any mystical appeal to special inexplicable operators of calculus. The first step is to stop blindly appealing to tradition in the name of rigor, right? We really need to stop doing this. Okay. Then we can notice that integration multiplies a function by the variable of the dimension we're integrating with respect to and the appropriate term of zeta, while differentiation divides the function by the variable of the dimension we're integrating with respect to and the appropriate term of zeta. Now, we should also note that each term of zeta is a unit fraction. What this means is that the multiplication we're doing has been normalized so that we don't have to manipulate the scale of any dimension except the one we're already explicitly working with. Or in other words, the numerator of d dx is obviously not a variable since it's unity in all dimensions other than x, as any other choice would just be meaningless. What this then allows us to do is notice that integration is simply multiplying by zeta x, and differentiation is division by zeta x. And if you so wish to interpret zeta as change in x per unit y and rename it d, then you simply get corrected Leibniz notation, where integration invokes times dx and differentiation invokes on dx. Now we should note where the numerator d in d dx came from in the first place. The simple example to consider is a linear function, y equals mx plus b. Here we can interpret b as the constant of integration and m as the slope, which is change in y per change in x. So now we get y equals mx plus b is identical to y equals x dy dx plus c. If we ignore the constant of integration and solve for x, we then get y dx on dy equals x. But y is our dependent variable, which means that we can never see how y behaves directly. So y and dy are actually indistinguishable to us, right? Because we can't tell how y is changing. And we can't tell that apart from y itself. So they end up being the same. Where x and dx are distinguishable, this results in y and dy canceling and giving us dx equals x. Now, what this means is that x is our independent variable, since we are allowed to manipulate x by changing dx. Okay? We're able to change this, and that influences this, because this is our independent variable. This is the thing that we're able to manipulate. At this point, we could rename z in the unified equation to d and almost get vanilla Leibniz notation completely for free as a side effect. Right? So if we do this, the only thing to tackle now is the integral sign. But that's frankly a triviality. What the sign indicates is an iterated sum. But by definition, that's simply multiplication. And specifically, it's the multiplication we're already doing. So it's redundant and confusing to even have it there at all. As such, the integral sign should simply be removed if we're being rigorous. And now you get this. A seeming issue at this stage is that a naive interpretation of the unified equation implies that these multiplications should not occur only on a term-wise basis, but across terms. Okay. The resolution to this is actually quite simple, but one I've only been using implicitly. And it's merely to note that d naught must itself be a single term, as any multi-term function we're attempting to perform calculus over is processed term by term, not as a whole. In geometric terms, this translates to the fact that the area under a curve given by a function is simply the sum of the areas given by the individual terms of the function, meaning that the sum of the terms does not yield any sort of special new thing, but is simply behaving exactly as any basic vector sum. And since the areas and slopes of these discrete components differ, that nonconformity forces term-wise processing. It's also worth noting that I chose the name zeta for the pure list of shape coefficients, because all classical zeta functions are actually a special case of it. For example, the Riemann zeta function, the Hurwitz zeta function, they're both simply special cases of my definition of zeta, and thereby this permits future simplifications to the philosophy and notation for anyone following the path I've laid out. And surely I've made mistakes, so yes, I encourage you to fix things. If we apply this over multiple different dimensions with k equals less than 1, we get the del operator, which hopefully you can now see is neither an operator nor particularly special. The Laplacian even makes it plain that it's simply a vector, since it's just del times del, which is the unified equation over multiple dimensions with k equals -2. Calling these trivial objects operators and surrounding them with esoteric mysticism is thus unambiguously a propaganda move, whose motive is to convey a false air of competence. Fundamentally, the nonconformity which appears between the components of del results from the nonconformities inherent between the terms of the base 1 polynomials which constitute del. This is naturally inherited by manipulations of del, such as the Laplacian and Hessian. But given the doctrines of logicism and the fact that the source of this internal structure is inexplicable from them, construing these things as platonistically mystical operators has really been the only option available. And then there's some examples here. I'm going to link this, so I'm not going to walk through all of these. But these are more or less full expansions of some examples. And then down here, I introduce the concept of floating point calculus. So, floating point calculus over sinusoids looks like this. The radix point in the above, we're simply indicating the alignment between the pieces. So see where the radix point here, it's right there. Here it's right there. Here it's right there. So we end up with different things happening. But here we're manipulating cos x and cos x. So that movement of the radix point is actually interesting. Okay, so note that establishing sin x as the de facto zeroth term of omega correctly renders both the zeroth term as perpendicular to dimension x and the first term of omega. So here I'm naming the objects slightly differently so that you can track whether we're working with trig functions or whether we're working with polynomials or what, right? So I'm not calling everything zeta. So here, this base 1 polynomial giving us the shape coefficients for cosine and sine, I'm calling it sigma, simply because that allows us to distinguish at other levels. And they're variables, so you can name them whatever the fuck you want. I don't care. And here I kind of replaced W with omega in the unified equation here. Yeah, so let's see. Floating point calculus implicitly invokes the unified equation. What this means is that the initial condition z0 is multiplied by all of the terms of the shape coefficient polynomial zeta for indices I from m to 0 inclusive, where zeta naught is marked by the radix point, and m is the index of z0 relative to this point. Thus, we get this. This naturally gives us both infinite sums and infinite products as a simple consequence of calculus as defined by the unified equation over the structures that we've demonstrated to be derivable entirely from first principles. It should be noted that this is the inverse of the classical interpretation, where it is taught that calculus derives from handling infinite sums and or infinite products. Of further note, one class of structures that this derives for us is those described by L functions such as the Riemann zeta function. And as a little dessert here, I've gone over the basics of this before, but yeah, you end up with this. So the Zermelo-Fraenkel axiom of extensionality, right? So two sets. So this is a little bit of a tangent to the calculus, but it does play heavily into the foundation, the problem with the foundation of mathematics, as established by the logicism. So, axiom of extensionality. Two sets are equal if they have the same elements. However you want to convey that, set theoretic notation, I don't give a shit, because I don't believe set theory is valid, so I don't care about that notation. Okay. The ordinals are composed of the naturals and have an inherent order within a specific dimension. The cardinals are composed of the naturals and have an inherent relative scale within a specific dimension. The nominals are composed of the naturals and have no order and no dimension. Note now, the ordinals, cardinals, and nominals are alleged to have exactly the same elements, and yet they are not equivalent. This violates the axiom of extensionality. This necessarily means that no logic which invokes the naturals, as they are classically defined, can possibly be consistent, since there must be a contradiction in the definition of the naturals, as we can see from this, right? The ordinals, cardinals, and nominals are all supposed to be made from the naturals, and anything made from the same elements is supposed to be exactly the same thing, but here, order, order, no order. Dimension, dimension, no dimension. This is a big difference. And this specific difference is what allowed Gödel's proof of incompleteness, using Gödel numbers, because Peano, Dedekind, Russell, Whitehead, they were all thinking of naturals this way, with that order, with that alignment to a dimension. But Gödel came along and used them as nominals, and that's how he showed incompleteness. It has nothing to do with, like, the operators of multiplication or whatever the fuck. It's because the naturals were built incorrectly. That had consequences when you came to multiplication. But the problems are apparent before that, well before that, if you know how to look for them. Okay, so this means that incompleteness does not necessarily apply to every possible logic capable of handling primitive recursive functions, since incompleteness is only proven for systems which invoke the naturals. This should be obvious since Gödel numbers are nominals, while Gödel incompleteness applies to systems built from the successor function. As it turns out, the contradiction is not difficult to spot, since the naturals are defined to be simultaneously unsigned, as they're claimed to precede sign, their signed counterparts being the integers, and positive, as they're claimed to be identical to the non-negative integers. If unsigned, they cannot have an order, but if positive, they must. Notably, the successor function is claimed to derive the naturals by way of accumulating positive units, which in turn forces both sign and order onto the naturals. And yet Gödel is accepted to have proven the incompleteness of precisely this system by invoking the naturals as unordered nominals. This is the definition of inconsistency. The naturals can be proven to both have and lack a specific quality, depending on the whims of the user, and yet the systems which Gödel's proof apply to are universally hailed as being consistent. If you prefer analyzing sentences in a language like Peano arithmetic, consider the following, keeping in mind that the orthodox interpretation of Peano arithmetic defines 1 + 1 = 2, yet this only applies to the first example. All right, so 1 dog + 1 dog is 2 dogs, so 1 + 1 is 2. This is what Whitehead and Russell proved. It went out to 1913, but whatever. 1 dog + 1 quail is 2 wings. So 1 + 1 is 2, but this is happening because we're saying that 1 = 0 and 1 = 2. The first one is 0 and the second one is 2. So we get 0 + 2 is 2. This is a 1 + 1 = 2, which is false under Peano arithmetic. 1 dog + 1 quail is 6 legs, so 1 + 1 is 6. 1 foot + 1 yard is 48 inches, so 1 + 1 is 48 because of unit conversion. 1/2 + 1/3 is 5/6, so 1 + 1 is 5 because of fraction addition. 1 frog + 1 pond is 1 pond, so 1 + 1 is 1 because frogs live in ponds. 1 stone + 1 mountain is 1 mountain, so 1 + 1 = 1 because mountains are made out of stones. 1 cup of water + 1 cup of dirt is less than 2 cups of mud, so 1 + 1 is between 1 and 2 because fluids fill the gaps between granulated solids. 1x + 1y cannot be simplified, so 1 + 1 is undefined because of like terms. 1 + 1i does not have length 2, so 1 + 1 is not 2 because of complex vectors. What this unambiguously means is that Peano arithmetic is neither consistent nor complete, because the Peano axioms never defined the naturals, but rather merely implied a vacuous correspondence between them and the set produced by the successor function, meaning that the properties of the naturals which allow them to be used as ordinals, cardinals, or nominals exist independently of anything established by the Peano axioms or Peano arithmetic. And notably, the alleged correspondence between S and the naturals, so S is the successor function, is one which does not actually exist, since the successor function is definitely ordered while the naturals are not. If the naturals were inherently ordered, then they could not serve as nominals. And yet Gödel's proof of incompleteness specifically rely on using naturals as nominals. This means that nobody working in mathematical logic has any qualms with the naturals behaving completely differently from the set produced by S, yet at the same time preach that the naturals are identical to the set produced by S. That's fucking weird. As such, none of the above listed results of 1 + 1 are ruled out by Peano arithmetic. If we're allowed to use the naturals as nominals, everything up there is totally fine. All of that is up for grabs. Since Gödel provides precedent for using the naturals in all possible ways within the context of PA. Thus, we have examples of 1 + 1 = 2 and not 1 + 1 = 2 being sound formulas of Peano arithmetic, but only 1 + 1 = 2 can be proven, even when it violates the Peano axioms as in the second example, while the rest are flatly disproven by PA. Given that all are sound under certain conditions, this is a ludicrous problem to have for something that has been so widely accepted for so long. Gödel leveraged the nominals to illustrate the incompleteness of systems like Peano arithmetic, but it should be noted that the majority of mathematics exists specifically because systems like this are pure and obvious nonsense. What this should indicate is that the mathematicians who have been in charge of defining what mathematical rigor is for the past 2 centuries are simply incompetent, since they're fundamentally unaware of how elementary mathematics even works. The core issue is that the naturals are an obfuscation of at least 2 entirely different structures. On the one hand, we have the named numbers that appear in most extant natural languages, not all. There are existing human languages that don't have numbers, and are used by those languages to count specific things. This structure is never divorced from dimension, right? So 7 on its own doesn't mean anything, while 7 bushels of apples, that does. And on the other hand, we have attempts at generalization by 19th century logicists who tried to claim that everything they touched was a number. And thus we have modern mathematics claiming things like -7, +7i, 7/3, pi, 7 plus 3i are all numbers. And magnitudes of vectors are inherently positive. Yet 7x plus 3y is an expression, and we're expected to accept casual refutation of the claim that 7 elephants is a number. Why are units randomly sometimes part of a number?